You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So, Shalom, I've got a puzzle for you.
Okay.
All right. In the podcast episode that we recorded last week, what was it that we talked about?
Well, we talked about different interpretations of quantum mechanics.
Right. So now tell me this. How do you know that that's what we talked about last week? I mean, how do you really know what happened in that session?
Well, I can remember it. Dan, is this really a puzzle?
Yeah, exactly. So, all right. So put that aside for a moment. And here's the second question. What are we going to talk about next week?
Well, we haven't decided that yet.
Okay. So you know what's happened in your past, but you don't necessarily know what's going to happen in your future, right?
Right. Though, again, I'm still not sure why this is a puzzle.
But shouldn't this be surprising? I mean, after all, for the most part, the laws of physics are exactly the same or just about exactly the same, regardless of whether you run them forward in time or backward in time.
Okay, I think I see where you're going with this.
So if I take the Newtonian laws of physics, for example, or Maxwell's equations that describe electricity and magnetism, or any of those theories, there doesn't seem to be any reason for time to point in one direction over the other. And that leaves us with a pretty big question. We can see that time does seem to point in one direction. After all, you can remember the past, but not the future. So what makes it point in that direction?
All right, so the puzzle is I can remember what we did last week, but I don't know what we're going to do next week. And that means that there must be something in the laws of physics themselves that differentiates between past and future.
Yeah, exactly. And we call this difference the arrow of time. But the reason that there's an arrow of time in our universe turns out to be pretty subtle. And I would say it's pretty interesting.
Okay, so today on our show, Dan and I are going to explore this puzzle, and we're going to talk about what it is exactly about the laws of physics that ensures that time really does move in one direction. We end up exploring everything from coffee and cream to what is life, so stick around. We hope you'll like this episode.
All right, so if you take the equations of things like Newtonian physics, including electricity and magnetism and stuff like that, those equations can give you solutions. And these solutions are all like physically possible things that might happen. It turns out, though, that for every single one of those solutions, if you take the symbol that represents time, we usually call it t, and replace it with minus t, you always end up with another solution that's acceptable to those equations. In other words, in the laws of classical physics, if they allow something to happen in one direction of time, it could also happen equally well in the opposite direction of time.
So one way to think about this is with an example like the Earth orbiting around the sun. If I took a video of the Earth's orbit and played it to you backwards, there would be no way for you to tell that it was backwards. The orbit follows the same rules of physics whether or not it's moving forward in time or backwards in time.
The same thing goes for projectile motion or any other sorts of physical situation you can imagine. Forward and backward in time are the same thing as far as these equations are concerned. Physicists would say that it's because these laws of physics we're talking about have a feature called time reversal symmetry. If you replace t with minus t in any of these equations, you get the same thing you started with.
This idea of a symmetry in physics is super essential here, so let's dig a little deeper.
There are a lot of kinds of symmetries embedded into the laws of physics. Time reversal symmetry is just one example. Throughout the 20th century, we've learned about other sorts of symmetries. One is called charge symmetry. The idea here is that if you took a bunch of particles with different electric charges and you replaced all the positively charged particles with negatively charged particles and simultaneously replaced all the negatively charged particles with positively charged particles, you'd be left with an identical situation. After all, electricity simply attracts particles of differing charges and repels particles of like charges. So by replacing positive with negative at the same time as negative with positive, you're really left with exactly the same thing. There's another symmetry called parity symmetry that's played an important role. The idea here is that something is parity symmetric if you take a mirror image of the thing you're considering, and it respects the same laws of physics. And I would say until the mid 20th century, physicists generally thought that the laws of physics would always be time symmetric, parity symmetric, and charge symmetric. But in 1956, experiments showed for the first time that the symmetry wasn't exactly respected by the laws of physics. The force that we call the weak nuclear force acts differently depending on the charge of the particle and depending on whether you're looking at a particle spinning in one direction or in the other direction. In other words, it depends on whether you're looking at something or its mirror image, and it depends on whether it's positively or negatively charged. So charge symmetry isn't exactly respected, and parity symmetry is not exactly respected. But even then, it was assumed that the combination of charge and parity symmetries would be respected until 1964, when experiments showed that this too is broken by the weak force. Now, there's this thing called the CPT theorem, charge parity time theorem, that says that the combination of charge parity and time symmetries has to be respected in any self-consistent quantum field theory, anything that respects the kind of laws of relativity and doesn't travel faster than the speed of light, things like this. So by learning that CP is violated, charge parity is violated, then we knew there had to be a violation of the symmetry of time as well.
So the weak force treats particles differently based on their charge and mirror image. So if I took a video of weakly interacting particles and played it to you backwards, you actually would be able to tell that it was backwards. Because in the backwards tape, the weak force would appear to treat positive and negative particles and mirror reflected particles differently, but in the opposite way than it normally does. So what this means is that the charge parity symmetry violation in the weak force necessarily means that the universe doesn't work completely symmetrically in time.
And you might think that this solves our problem, our puzzle at the beginning of the podcast, that it seems like nature differentiates between forward and backward in time. And there is a small difference here between forward and backward in time, according to the weak force, but doesn't really solve the problem. It turns out that the stuff we observe, the fact that I can remember the past, but I can't remember the future, doesn't really have to do with the weak force at all. As far as the arrow of time is concerned, we need something else to explain it.
So in other words, the weak force shows that there's some difference between past and future, but it doesn't actually tell us why time moves from past to future.
That's right. There's nothing we know about in the, all the way down the fundamental laws of physics that should tell us which direction through time we would perceive as being forward.
Okay, so to figure out this actual arrow of time, we need to look somewhere else.
Exactly. So it turns out we understand now that the arrow of time, the perceived direction that we call forward in time, has to do something called the second law of thermodynamics. So what the second law says, well, I should say the first law is really just energy conservation. So
yeah, no one ever talks about the first law.
It's just not as exciting. Second law is where all the romance is. So what the second law of thermodynamics says is that the total entropy of any closed macroscopic system will never decrease. I should add a little caveat there. Will almost never. It's a statistical law, it turns out, but it will almost never decrease. It will either stay the same or it will increase. Now, let me say a little bit about what entropy is, because everyone uses the word entropy in certain circumstances, but physicists mean something very specific. Entropy is a way of measuring the disorder of a system. So, for example, like a classic example of entropy is if I have a cup of coffee and I pour some cream into it. Initially, the coffee is kind of in one part of the coffee cup and the cream's in another. before they have a chance to mix. This is way out of equilibrium. An equilibrium state is where that coffee and cream totally mixes together. And as far as entropy is concerned, you start with a really low entropy state when the coffee and cream are separated, and then it moves towards a high entropy state when they're totally mixed together. So basically, as the coffee and cream mix and the system gets more disordered, the entropy increases. And this has everything to do with some processes being reversible and some being irreversible. There are a lot of processes in nature, like planetary orbits, that could go in either direction. In those sorts of processes, the entropy stays the same all the time.
And in those sort of processes, there is time symmetry.
That's right. Time symmetry is totally observed. You can see a video of it going in either direction, and you can't tell which one is the real one. But that cream mixing with coffee, that is a very irreversible system. You will never see cream and coffee spontaneously segregate themselves inside a coffee cup. That will just never happen. So that's an irreversible process because the entropy changes going from one to the other. So the modern definition of entropy was laid out in 1877 by a physicist named Ludwig Boltzmann. He said that, sure, you can think about entropy as a measure of disorder, all that's correct, but if you want to really be precise about it, if you want to be quantitative about it, he said you should think about entropy in terms of how many different ways at a microscopic level you could create something that looks qualitatively similar at the macroscopic level. In other words, how many microstates correspond to a given macrostate. So going back to that coffee and cream example, there are many, many, many more ways you could combine a bunch of coffee and cream molecules to wind up with a thoroughly mixed cup of coffee than there are ways in which the coffee and cream will be spatially separated. So for this reason, there's a much larger amount of entropy associated with the mixed macrostate as the separated macrostate. This is why, he explains, nature tends to move from separated coffee and cream to mixed coffee and cream. I like to think about entropy in the context of dice rolling. So imagine you roll 3 six-sided dice. Maybe a microstate could be something like a 2 on one die and a 4 on one and then another 4. So the microstate is 2, 4, 4, but the macrostate is the sum of the 3 die, or 10. Turns out that there are 27 different ways to roll a 10 on 3 six-sided dice, and only 25 ways to get 9. There are only 3 ways to get a 4, and only 1 way to get a 3. Because there are the most ways to roll a number like 10, this is one of the highest entropy states. And because a 3 is one of the least likely things you could have rolled, this is one of the lowest entropy states. Now imagine that I start with a configuration of these dice where they're all facing with their one side up, so a total of 3. So this is the lowest entropy state, or one of the lowest entropy states. Then I pick one of the die at random and I re-roll it. Probably 5 out of 6 times, the total is going to move from 3 upward toward the maximum entropy state. In other words, there's a good chance that this low entropy state will move towards a higher entropy state. And then I pick another die and I roll it, and I pick another die and I roll it, all at random. What you're going to see is that the system is going to gradually evolve from the lowest entropy state, statistically speaking, towards the highest entropy state, towards something like 10 or 11. And if I waited a long time rolling these dice one after the other, there's a pretty good chance that when I'm done this a long time, I'll get an answer somewhere close to 10 or 11. After all, there's like a 50% chance that the dice will be somewhere between 9 and 12. This is just because there's way more ways to roll 9, 10, 11, or 12 than there are to roll 3 or 4 or 17 or 18. This is just the arrow of time at work. Even though there's nothing about the laws of physics that favor one die configuration over the other, statistically speaking, you expect the low entropy state to evolve to something like the maximum entropy state.
So it's not that there's some kind of fundamental law of physics that prefers the dice to add up to 10 rather than 3. It's just the effect of statistics. And so this kind of begs the question, is the second law of thermodynamics actually a law of physics, or is it just a statistics law?
Well, that's an interesting question. I mean, the dice rolling seems to be dictated by Newtonian dynamics, and there's no arrow of time built into that. But at the same time, you could think of the second law of thermodynamics as being a law of physics, but one that tends to take low entropy configurations and drive them towards high entropy configurations without anything in the underlying equations of Newtonian physics driving that. It happens for other reasons that don't have to do with the equations that are working on it.
So it seems like the answer to this question just depends on your philosophy of what a physics law is.
Yeah, I wonder what historians of physics or philosophers of physics think about that. I've never given it a thought about whether the second law is really a law of physics or not. That's interesting. So taking this dice analogy even further, now instead of rolling 3, let's say you're rolling a million six-sided die, okay, all at once. And instead of rolling them at random, let's have them all start out with ones facing upward. So you have exactly a macro state of 1 million six-sided die, all with ones facing up. And then we're going to pick a die one at a time and roll it. And over time, doing this, millions and millions of times, we tend to evolve from a macro state of 1 million towards a macro state of right around 3.5 million. It will vary a little bit, but there's no question that after you've rolled these dice, hundreds of millions of times or something, you'll have a number pretty close to 3.5 million facing upward. Now imagine I showed you a video of this. You don't see the hands in the rolling, but, maybe a sequence of pictures of the dice and what's facing upward. You would have no problem figuring out which of these two directions was forward in time. You know that if you started with a random configuration of dice and you started rolling them at random, they don't all evolve towards all ones. That would be exceedingly unlikely. This is the second law of thermodynamics. This is the arrow of time, differentiating between forward and backward. So we can extend this analogy to a circumstance involving a large collection of atoms. Of course, there are many, many more ways to arrange coffee and cream molecules together so that they're all blended than there are ways in which these two components could be neatly separated from one another. From this perspective, the tendency for cream and coffee to mix into each other is just a simple consequence of there being far more blended microstates than there are separated microstates.
And going off of that, if you think about the very specific arrangements of atoms that you need for something like you or me, Dan, to exist, right? Any kind of life, really, that's a really low probability arrangement. There are so many more ways that you can organize atoms to be like a big clump of stuff than to be a human being or a dog or a cat.
Yeah, I mean, if you took a truly random configuration of atoms, there is a vanishingly small probability that it would make anything that can do all the complicated stuff that living organisms can do. I mean, even if you're talking about some simple single-celled or bacterium or virus or something, that's exceedingly unlikely that you could just throw stuff together and wind up with that. Anything that would be capable of processes like metabolism or any kind of processing of information, this has to be an incredibly low entropy state.
And not only that, but if you think about it, it also seems like as humans, we possess the power to lower the entropy of a given system. After all, I can pick up all the dice and set them to face 1, thus putting this whole die system in a lower entropy state. Does this mean that humans violate the second law of thermodynamics? Well, no, we don't. So there's a catch that I didn't mention, which is that for me to be able to go pick up those dice and move them around, I have to be exerting my own energy. And the energy it takes me to do that ends up radiating in the environment in the form of heat. So even though I can lower the entropy of the die system, the entropy of the entire system, with me and the environment included, still has to increase.
So even if we can use energy to artificially lower the entropy of some system, we're actually creating more entropy in the overall surrounding environment. So the total entropy of the closed system always goes up or stays the same following the second law.
This idea is shown through a famous thought experiment called Maxwell's demon.
So the idea is you take a box and you put some gas in the box, and then you separate it down the middle. You put some sort of partition that keeps the gas in two different compartments. And then you open a door between the two sides whenever that door would allow a high energy particle of the gas to move from one side to the other, or a low energy one to go in the other direction. And if you open and close the door at like smartly chosen times, at precisely chosen times, you can wind up with a situation where all the fastest particles, all the high energetic particles are on one side, and all the lowest energy particles are on the other side. This is kind of analogous to separating the coffee from the cream in a coffee cup. And this would seem to violate the second law. And people worried about this at the time. But it was eventually showed that the energy you would need to open and close that door repeatedly would produce more entropy than you actually reduced the entropy of the box by. So in the end, you can't actually break the second law with clever partitioning or other sorts of actions you might take on the system.
But even though we don't actually have the power to reduce the entropy of the universe, I still think it's pretty interesting and illuminating to think about life as a force that resists entropy in some sense. And it turns out I'm not the only person who thinks like this.
In the 1940s, the quantum physicist Erwin Schrödinger wrote this very surprising book, a book you would not expect a quantum physicist to write, called What is Life? It's one of my favorite books of all time. To this day, I just love it. I reread it every few years. And among other things, he proposed in that book a definition for life. And he doesn't make any reference to reproduction or metabolism. The kind of stuff that you find in biology textbooks is not what he's talking about. He simply says that something is alive or something is living if it keeps itself in a low entropy state through the use of free available energy. And if you think about it, I mean, anything that's doing metabolism or anything that's doing any kind of information processing is doing exactly that. They're keeping their system in a low entropy state by using energy. So as far as the existence of life itself goes, it would seem that, the second law of thermodynamics should be working against that. And in some sense it does. But the forces of Darwinian natural selection are essentially reaching into nature and reducing the entropy of individual systems while increasing the entropy of everything else. So in our analogy, it's like the Darwinian natural selection is reaching in and turning dice from one number to one, from other numbers to one, keeping the entropy of those organisms low. Darwinian evolution can only work and only accomplish this when there's free energy available. So it can't work in environments that are in equilibrium. There have to be things like starlight or whatever, some sort of freely available energy that you can use to keep the entropy of some specific organisms low. And this process invariably causes the total entropy of the universe to increase, even when it keeps the entropy of those individual organisms that it's acting on as low as possible. So life is entirely consistent from this perspective with the second law.
So, if you'd like, you could define life as being the ability to control and lower the entropy of some system. But there's always a total increase in the entropy of the entire environment.
Exactly. Yeah. So we take sunlight, which is pretty low entropy when it reaches us. We absorb it, we use its energy for stuff, and we radiate heat away, which is much higher entropy. So we basically, cannibalize off the low entropy of starlight to be able to do all the cool stuff we do. So I'm a cosmologist, and from that perspective, there's some interesting questions raised by the arrow of time and the second law of thermodynamics. After all, we've seen our 13.8 billion year cosmic history since the Big Bang. There has been an arrow of time the whole time, and that means the entropy of the universe has steadily increased as our universe has expanded and cooled. But that means that if our universe is to be in the state we find it in today, it must have been in a very, very low entropy state in the Big Bang. And we don't know how or why it wound up in such an unlikely state. It's kind of like saying that our universe's dice were all facing 1 shortly after the Big Bang. And we don't know why. We don't know how they wound up that way or what physical mechanism might have led to that. If you'd like to learn more about the arrow of time, there's a book I really want to recommend to you. Sean Carroll wrote this great book some years ago called From Eternity to Here. He touches on all the ideas were talked about in this podcast and digs a lot deeper into them. So that's my shout out to Sean and this great book.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jay Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.